All right, so like I said earlier, we're going to take a look at this limits day one, just this problem right here, before we get into the nitty gritties of like, how do we do the course? Let's start off with like what we're going to be doing. And so our very first unit is something called limits. And we do have a textbook, which we'll talk about in a little bit. I don't particularly love the way the textbook sets it up, but this is the one unit where I will go sort of out of order, okay? So if you're a very like, but I like to know what section we're on, that's not going to happen for limits, but I do kind of tell you where to find things. But the rest of the units will be like by the section in the textbook, okay? All right, so here we have this graph. For some of us, this may be the weirdest looking graph that we've ever seen. Maybe we've never even seen anything like this, okay? But before we even look at the questions, let's kind of look at the graph a little bit more carefully here. What are some weird or maybe like things that we don't see normally in a graph, like things that are not as common when we think about a regular graph? All right, Marilyn, I see that we have some holes. Can you give me the X value of where you might see a hole? Great. All right, so maybe around like negative 3.5. Looks like there's a hole in the graph. Excellent. And Marilyn also says that at X equals 3, it looks like there's a hole in the graph. Okay. Now, in looking at these two, would we say that these are the same kind of hole, or would you say that they are maybe different kinds of holes? And anyone can answer this. All right, Dallas says different. What makes you say that this is different? That these two are different from each other? Okay, great. So in the chat, Dallas has said at X equals 3, the 3 actually has a dot somewhere there. But like at X equals negative 3.5, it's just the hole, there's no dot. Okay. All right, what are some other weird things that are happening on this graph, or things that maybe we've not seen? All right, I see Enrique says different due to the curve shape. Okay, yeah, I know that like this side of things is a line, right? We know how to graph a line, but then all of a sudden it's like, I don't want to be a line anymore, but I'm going to do some polynomial curvy type stuff going on over here. Okay, yeah, exactly. So Enrique, that is a great observation. Sometimes we call this a piecewise function. Right. And a piecewise function just means that we take like different types of graphs and we sort of glue them together, right? So we have a line on this side, and then next to it, we sort of glued a polynomial situation. Okay. All right. And that is absolutely fair, Marilyn. It is 9:52 in the morning. I don't know how many people have had their coffee yet. I am not, but I also am not always like a huge coffee drinker. So we'll see how it goes. But yeah, there is actually at X equals negative 1. There's a hole right here. Right. So maybe we can go back and mark this negative 1 as a point that is like kind of interesting to look at. Now, earlier, Dallas had pointed out that like this hole is just a hole. And then this one had like a dot above it. What do we think? And I'll put this question out to the whole class. Do we think at X equals negative 1, it's the same kind of hole as the other two, or do you think it's different? All right, we've got 2 votes for different. By the way, 3 votes for different. I know that folks are posting to the whole chat. If you feel uncomfortable about that right now, because you're like, we just met, I don't know everyone in the class, you can also send me a direct message with your vote. All right, so we've got a few that are different. We have one that is the same. Okay. Enrique, I'm curious, what makes you say that this is the same as the other holes that we see here? Okay, it's part of the same line. Do you mean that like this dot is like on the line? Is that what you're saying? And then like this one is on the curve part? Both holes are connected to the same line. Yes, and by the way, you can also unmute if you're like, I don't really feel like typing this in. Math has a lot to type. You can absolutely unmute, whatever makes folks feel comfortable, okay? So, anybody has any last thoughts about these three places where there are holes? Okay, so at this point, I don't think that we have any answers per se, okay? So I know some of us are like, well, what is the right answer? Are they the same or different? I think what I'm trying to get us to do, especially because it's our first meeting time together, is just to really think about like, what do we see, right? What do we see and what are we curious about? Right? Like if I'm looking at this, I'm like, this is a line, that's not that interesting, but then there's a hole. That's weird. That's interesting. Let's think about that, right? And then looking at this point, that looks, I don't know, maybe it could be the same, maybe it could be different. I'm not sure yet. And same thing here, maybe it's the same, maybe it's different. I'm not sure yet. But over the next few weeks, as we talk about limits, we're going to unpack some of those answers. Okay. And so I think what I'm asking you for actually is quite a bit of trust to say, like, we're going to get some answers eventually. But I really like to see like what our thoughts are before we jump into like math that, you know, and all the rules and everything. I really want us to think about where things come from. Okay. So thanks for humoring me with like, let's look at the picture and see what we think. But underneath here, I have a few questions. All right. And so this is a structure that you'll see pretty frequently. I typically like us to start with something like what we know. Okay. What we know could be stuff that maybe we've seen in like trigonometry or pre-calculus or algebra. Okay. And I want to make one thing really clear here. Even though this says what we know, if you're sitting like in the privacy of your own learning environment being like, I don't know this, that's okay. This serves two purposes. One is to kind of like trigger previous memory, but the other piece is like, this might be something we use. So let's refresh it for all of us together so that we can sort of walk into this what's new piece together. Okay. And so let's take a look at these what we know questions. And I'm going to ask us to focus on this first one right here. It says F parentheses -3. Can someone say what that is asking us for? So like not what the answer is, but what is that question asking us to find?
When -3 is plugged in as X, what is Y?
Wonderful. All right, I don't know why I chose this aggressive hot pink color to start with, but that is exactly what this means, is when X equals -3, what is Y? Okay. Perfect. Thank you, Marilyn, for putting that in the chat. All right, so according to our graph here at X equals -3, what is the Y value that we have? All right, I've got one answer as a 0. Let's see. Got a couple answers as a 0. Got a 2. We're looking for -3, not +3. Okay. Yeah, so I think we all see that we're looking at -3, which is right over here. Yep, exactly. And that Y value is 0. Wonderful. Okay, great. So then this question, F of 0, is asking us, when we go to an X value of 0, what do we get for the Y value, right? And so what would we say based on this? Like if we were to estimate, give an answer, what might we say? All right, I see a 0.5. 0.5, 0.5. Yeah, like right over here, it kind of looks like a halfway, right? If you were to say 0.6, I would buy that too. If you were to say 0.4, I would buy that too, right? So like sometimes when people ask us to estimate, maybe we've had that math teacher in the past who's like, but I need it to like 17 decimal points. If we're estimating on a graph, right, and there's no lines that would tell us otherwise, it's okay if we're like, it's like 0.5-ish, right? That's okay. All right, last but not least, looking for f of 3. What do we think? What is the, when x equals 3, what is y? Oh, this is good. This is good. Okay, so I'm looking in the chat and I'm seeing some folks put in 1 and some folks put in 2. Okay. Those are really good choices. Those are really, really good choices. Okay. So can someone who's put in a 1 maybe unmute themselves or put in the chat like why they think that that y value is 1?
I was just following the pattern.
Okay, can you tell me a little bit more about that?
Like how we did the previous two, and we just went like up to the line where it's crossing y. So at 3 you go up the first like hole that I see, it's at 1. So I just went with 1.
Great. Okay. I love that reasoning. Now that's going to be something that I ask us to do quite a bit. And so for those of you who had me before, you're like, yeah, she's going to ask you to explain your thinking. Yeah, I'm going to ask you to explain your thinking. Okay. And part of that is because no matter what you use about math, you may or may not use math in the future, but people are probably going to ask you to be like, well, tell me why, right? It could be just like a conversation you're having with someone, or you're trying to argue a point for something. And so having that skill of being able to explain what you're thinking or why you're saying that, whether you're incorrect or correct, is really valuable. And so I completely see that, right? You've got this curve, we're following along the curve. Makes sense that that could be 1, right? Okay, can I get someone who voted for 2? They said that the y value at x equals 3 is 2. Can I get someone from that camp to unmute and maybe explain why they think that?
I'll go if that's all right. I personally would think that it's 2 because of the fact that the whole means and a solid dot means that it's an actual value in the position.
Ah, okay. So I think this is one of the things about these sort of weirder looking functions where this notation where we have a filled in dot is maybe a little out of context for us. And I would say that one thing to keep in mind is that even though this is like a solid line here, right, this part right here, it's actually made up of an infinite number of solid dots, right? Solid dots. But if it's an open circle, all right, that's actually where we're like, oh, that's not the value there. This is almost saying like, oh, we took that 1 point out. Maybe it was there before, but we picked it up and we moved it somewhere else. And in this case, we happen to move it up to 2, okay? And so f of 3, when x is 3, what is y? It's actually going to be 2, okay? Maybe we leave a note for ourselves here that this is 2 because we go for the filled in dot, not the open circle. All right, so the filled in dot, not the open circle. All right. So what's new? All right, so things that we know, reading points from a graph. I would expect that these first two, I'm so glad that that went really well for us. I'm so glad we had a conversation about the third one, like which one is it, right? But what's new is we've got this like thing, LIM, and then underneath it, there's like an X and an arrow and a number. And we have this like f of x notation. We're actually going to come back and we're going to answer those later. Okay, so we're going to come back by the end of today. All right, by the end of today, I hope that this notation that might look really scary to some of us right now is actually going to be something that we're like, oh, okay, I feel like I know what this is asking and I know how to read a graph to get to that point. Okay, so that's where we're headed right now. We're not going to put in any answers for that, but these kinds of questions look a little bit different than these kinds of questions. And so we're really going to unpack the difference between those two. Okay. All right, so I'm going to pause this recording for a moment. All right, so before we took some time to get to know someone else in our class, we were taking a look at this picture and we were answering questions that hopefully seemed a little familiar, where we've seen this function notation and talking about like, how do we know what the y value is, right? And I would say the most important takeaway here is that something that's sort of like a weird looking situation, we want to go where the filled in dot is when the question looks like this, okay? Did that just stop sharing? Yeah, okay. Let's try this again. You know, I feel like I found a lot of things that I like about the, virtual teaching. Like I love having notes to be able to post and all of that. And sometimes when the technology is not behaving itself, it can be a little less exciting. Okay, so let's start off with this. What is a limit? Okay, so when we think about the notation, we're going to be looking primarily at things that look like this. Okay, and I remember the first time I saw this notation, I was like, why are there so many letters? Like, what is happening? How do I read this? What do I even know is the answer, right? And we're going to find that there's going to be a lot of decision making we need to do. Today, we're going to look at how to find it on a graph. We're going to learn how to find it using some algebra. All right, so to kind of think back on some of the algebra skills that'll be really important throughout the semester. But at the very least, right, before we can talk about decision making or anything like that, it's important that we know what a question is even asking, or like what our answer should look like. Okay. So when you see something like this, this is how we're going to read it, okay? We're going to read it like this. The limit as x approaches a, oh, let's use a lowercase letter here, Judy. All right, the limit as x approaches a of f of x is L. Okay, so this sentence says the same thing as all those symbols right there. Now, I'm a really big fan of color coding. It helps me understand things a little bit better. But the limit part in the sentence, I got that from the LIM part there, okay? So the limit, now where did I get the x approaches a from? X approaches a is how we would read that x arrow a, okay? So far, what's happening is we're getting close to some x value, okay? Now, what picture are we looking at? Well, we're going to be looking at a specific function. All right, so that is our f of x. And our answer is going to be the limit. All right. Now, this L here, all right, this capital L is, in fact, a y value. All right. So earlier we were like f of 3, f of -3, f of 0. We were looking for y values. We're still going to be looking for y values. Okay. So at the end of the day, we're still looking for y values. The thing that makes this different is we're looking for y values as we get close to a specific x value. Right? The key word here, we are getting close to a specific x value. All right? It almost doesn't matter whether we get to the x value or not. We just want to get really close to that x value. Okay, and that's the part that makes things a little bit weirder for the brain. All right. But let's practice this. Let's take a look at some pictures. And now we're going to be trying to answer these questions about what happens when we get close to specific y values. All right, or close to specific x values. All right, so let's take a look at this example. All right, so how do we find limits? And the first way we're going to look at this is graphically. We're going to look at how we find limits from a graph. Okay, so here is our picture. All right, this is the picture that we're going to use. And if you were to just look at the picture right now, and just like we did for our warm-up activity, can you tell me some x values that feel a little weird? Yeah, maybe at like x equals 0, some weird stuff is happening, like we've got a hole there. All right, Dan, I see that you're saying at x equals 2. But there's some weirdness happening. There's a hole, right? Yeah, I would say that out of all of the things happening on this graph, those are exactly the 2 points that we want to be like, some weird stuff's happening here, okay? And it turns out that this entire first part of the question is asking us about what happens when we get really close to x equals 0. Okay, so for A through D, we're going to focus on what's happening here. Okay, so let's take a look at this question. The limit as x approaches 0 with a little minus sign. That is like the tiniest minus sign. That minus sign. Okay. The limit as x approaches 0 with a minus sign of f of x is, and that's what we want to answer. Okay. And so just for this section of the notes, I wrote it out in words what we're looking for because this is so new for us. Okay. So we're trying to find the y value that the function gets really close to when x approaches 0 from the left. Okay. This little minus sign that I highlighted in the yellow, that little minus sign in the place where there would be like an x squared, right? The little 2 in the squared, or like a little 3 in a cube. That little minus sign tells us we want to come from the left. Okay. So let's go back to our picture for a little bit. If I have x equals 0 and I want to come from the left, I'm going to start on the left-hand side and then trace the function to get close to x equals 0. Okay, so I'm going to start tracing over here, tracing. What y value am I getting close to? Yeah, I'm getting close to a y value of 1. Did I get to 1? No. Okay, this is the weird part. We don't get to 1, but we don't care about that. All we care about in this question is, what are we getting close to? It's getting real close to 1. That is enough for us to answer this question. And so our answer would be 1. Okay. Now, on a lot of your, like if you look at textbooks or you look at some of the quizzes that we're going to do over the semester, I'm probably just going to give you this part, just the notation. Okay. But what I think is really important is that when you read that notation, you can think about what it's really asking. All right. So that's why I have the sentences here. Okay. So we've traced from the left and we get close to 1. All right. Let's take a look at question B. It looks almost exactly the same. What is the small difference here? Bingo, right? Two answers that work very well together. We have a plus sign here. And just like Jordan says, that means we are now going to start from the right. Okay, we're going to start from the right. We're going to trace our picture. And so if I trace it, I'm going to see that we get something like that. What y value are we getting close to? Okay, so I think sometimes it's a little better when I use the laser so we can see like the direction that I'm going, but I want to go in the direction towards 0, right? Towards x equals 0. And so when I'm going in that direction, the y value gets really close to 3. Does that make more sense? So maybe instead of highlighting, maybe if I did this, like I'm going this way, going in that direction. Okay. And so we can say that the y value that the function gets really close to when x approaches 0 from the right is 3. Okay. Yes, what's up?
Because there's a solid dot, wouldn't you say that y equals 3 though, at 0?
And so here's the other weird part. It's okay if we actually get there, but it's also okay if we don't actually get there.
Got it. That makes sense. Thank you.
All right, so let's take a look at question C. All right, so question C looks almost like the other parts, but this time there's no plus or minus. There's no plus or minus, okay? So when there's no plus or minus, it really means the y value that the function gets really close to when x approaches 0. But this time, we're coming from both sides. Okay, we're coming from both sides. What value did we get when we were coming from the left? We got 1. What value did we get when we were coming from the right? We got 3. Now, this is not a trick question. Is 1 equal to 3? No, right? Not in the context of what we're doing. In a different kind of math, sometimes 1 is equal to 3, but that's a different story for a different time, okay? So 1 is not the same as 3. 1 not equal to 3, I don't get to the same point. I don't get to the same y value. So the way we write that is, let's see, the y value that the function gets really close to when x approaches 0 from both sides is different, okay? And because it's different, we're going to call this, we often say, does not exist, all right? I feel like at this point, this movie is a little bit older than I really wish it were, but how many of you have seen Mean Girls? Yeah, it's okay. You don't have to admit it if you have, but I've seen it. It's a funny movie. But at one point in the movie, right, like she's this math nerd, she's like answering all these questions and she's like, the limit does not exist, right? All that means is that when you come from different sides, you're going to get to different values. So we can't say that there's one answer, okay? And so that's what it means when it says the limit does not exist. But because this happens when we look at sort of weird graphs, sometimes we just abbreviate it as D and E, okay? D and E does not exist. But the reason we write does not exist is because we get to different values, okay? All right, we've got one last question here, which is f of 0, okay? So f of 0, well, that's actually like our what we know, right? Someone said it so well earlier. They said f of 0 would be saying like the y value of the function when x is exactly at 0. Okay. And Nora, I think you actually have answered this question already, but anyone can answer this. What is the y value when x equals 0 for this particular picture? Bingo, right? Turns out that's where that filled in circle is. That's where the filled in dot is. So that is how we know what the actual y value is, all right? So let me pause here for a moment. How are we doing with the graph and the pictures and all the notation? Because there's a lot of notation going on here. I see one good. We have so many of us in here. It's okay if you're not feeling good about it yet. We will do another example. But... all right, so let's do this. Our peer mentor is in this space, and I'd love to hand the mic over to him for just a second. But before we do that, can everyone in the chat, all right, send me a message, just me, that is either 0, like I don't know what I'm doing right now or what's happening, or a 1, like yeah, this sort of makes sense to me. All right, so all you're sending me is a 0 or a 1. Decimals are acceptable. Fractions, it's like, I mean, be a total math nerd if you're sending some fractions, and I would love that. All right, cool. Great. All right, well, we're going to do another example in just a little bit, but I'm going to pass this over to Yitan for a second. So I'm going to stop sharing my screen. And let's pause this recording. All right, so we're going to take a look at the same picture, but as folks accurately predicted, whether you knew it or not, the other sort of weird point here is happening at x equals 2, okay? And so we're going to try the same thing where we're going to talk about what happened. Oh. we're going to talk about what happens when we approach from the right and from the left and get a second chance at seeing the differences. Go. Great. Okay, so we're going to get a second practice at talking about what it looks like when we come from the left or the right for any given function. Okay, so in part E, we're going to take a look at the limit as we approach 2 from the left. Right. So I'll give you a moment to take a look at that. And while you're looking at that, let's also take a look at what's happening when we approach 2, but from the other side, the plus side, the right side, okay? And so I'd like us to think about this, all right? Let's think about this for about 30 seconds, right? When we look at this graph and we're approaching 2, but we're coming from, let's see, the left-hand side, and then as we're approaching 2, but coming from the right-hand side, okay? Take a moment, and in the chat, but don't hit send yet, I'd like you to type same or different, okay? So don't hit send yet, but same would mean, I think that the limit from both sides is gonna be the same. And different would mean, I think when we come from the left, we get to this value, but like if we come from the right, we get to a different value. Okay, so same means we're gonna get to the same Y value, like the answer for part E and F would be the same. Different means that the answers for E and F would be different values. We would have different numbers, okay? So go ahead and type in same or different. And 3, 2, 1, hit enter. Excellent. All right. It looks like most of us are saying same, and that would be exactly correct. And in fact, what Y value are they both going to? Yeah, exactly. They are both going to 5. Okay, so we can fill in, oops, not there. 2 from the right also gets close to 5, okay? That's excellent. So sometimes that happens, right? Sometimes when we come from both sides, from the left and from the right, we get to the same Y value. That actually helps us answer part G, okay? So part G, oops, different blue. Part G is saying, find the limit from both sides, okay? So when we approach 2 from both sides, we get the same Y value. And in fact, because we get the same Y value, we can say, yeah, the limit overall is just 5. Okay, so let's just zoom in for a moment. Ooh. In part C up here, they were different, and so we said does not exist. But in part G here, we have that they're the same, so the limit does exist. Okay. If your answers from the left and the right are the same, that gives you your answer for the overall. However, if your answers are different from the left and the right, you're going to get a does not exist. Okay. All right, the last question on our graph. It is a return to things that we know, function notation. And this says, find the Y value of the function when X is exactly at 2. What's the Y value when we get to X equals 2? Not like we get close to it, but like we're actually there. Okay. Oops. there's a hole right here. That means there's no value right there. What if I did this though? I drew in a point right here. How would that change your answer for H? Yeah, exactly. That would be 3. Exactly. Okay. So if I had a dot like up here, maybe I would say that's 7, right? Or if I had one like here, maybe I would say that's 4. But since it's an open circle and there's no filled in circle, we actually say that this is undefined. Okay. Undefined and does not exist, depending on who you ask, can mean the same thing or can mean different things. I think in this class, we're going to use them a little interchangeably. So sometimes we'll see undefined, sometimes we'll see does not exist, but typically we use does not exist when we're talking about limits. And we use undefined when we're talking about an actual value. Okay. All right. So there is a quiz that is due at the end of this week. And I know we haven't really talked about that yet, but every week you will have a quiz that is due. The word quiz can sound sort of scary, but it's only meant to be scary in the sense that you really should do it. If you do the quiz and you understand things on the quiz and you can sort of like do this thing where you're like, well, what if there was a point here? What if there was a point up here? Like ask yourself those what if questions. They're meant to be really supportive in helping you be as successful on an exam as you want to be, okay? That's the only reason I call it a quiz. Other than that, the expectation is that you collaborate with people, that you work with each other, that you work with Ethan, that you work with me in any sort of capacity to help you really understand that. Okay, so it's not like a closed notebook, like just sit down and do it. In fact, I know some students in the past, because I do post the quizzes early at the beginning of the week, they'll look at the quiz. And then as we're going through the lesson, they're like, oh, this is number 1 on the quiz. This is like number 2 on the quiz. And then at the end of a lesson, they actually know exactly which questions they know how to do already and which ones they still have questions on. Okay, so for those of you who are like, yeah, I really want to be successful, I know that's a strategy that's been helpful for students in the past. Okay. All right, but let's keep moving. We've got our graphs. Graphing is one way that we can find limits, but it turns out that sometimes we don't have a graph. And so we're going to spend some time taking a look at what it means to find them algebraically. Okay. So we're going to start with the best way to start. It doesn't work all the time, but sometimes questions might look really complicated. And if you start with substitution, you'll actually end up with an answer without going through all the other complicated things we're going to look at. Okay. All substitution means is when you see a question, and we're going to focus on examples 3 and 4, you should try plugging in the given x value. Try plugging in the given x value. Here's why that's a really good strategy, okay? If I scroll back up for a moment and we look at this graph again, remember I asked you to tell me the weird points and you were like, there's this weird point and this weird point. There were 2 of them. But there's so many points here that are actually not weird. Okay, there's so many points that are not weird that chances are we might get one of those points. And so if we look at the non-weird points, all we're doing is just plugging in the value, okay? In other words, we're saying, let's see if this is the same as f of 5 in the first one. Instead of saying, what happens as we get really close to 5? Let's say, what happens at 5? That's really close to 5, right? Let's try that first. So let's plug in 5. And we'll get 2 times 5 squared minus 3 times 5 plus 4. Do a little bit of mental math. I feel like the further I go in math, the worse my mental math gets, but let's just give it a go. What do I do first here? Do I multiply the 5 by 2 or do I square it first? Yeah, we're going to square it first, right? We're going to use that. So we'll get 2 times 25 minus 15 plus 4, right? So we get 50 minus 15 is 35 plus 4 is 39. Okay. Can anyone tell me what shape this graph is? Yeah, this, my friends, 2x squared minus 3x plus 4 is indeed a parabola. We know that because of the x squared. And whether we liked parabolas or not, they kind of do look like this U shape, right? And if we think about most of the parabolas we've seen, there's no like, oh, it's missing a hole or we like put a different value somewhere else. It's like a very, I mean, I don't want to say boring, but like, you know, just kind of you plug in the value, you get the point. That's it, right? And so getting a value out here makes sense. And as a friendly reminder, 39 is a y value. Right? That's what we're doing. When we get to the end, that answer for our limit is a y value. Okay, well, this graph, I would be surprised if you were like, oh yeah, I totally know what that looks like. Okay, so it's okay that we don't know what this one looks like. But sometimes when we see things that are more complicated looking, we sort of panic and we're like, the question looks hard, so clearly I'm going to need a more challenging method to solve it. But be patient with yourself and just see, is this the same as f of -2? Just see, right? Because no matter how many weird points there are, it's more likely, probability-wise, that we're going to get a non-weird point. Okay. So give you a moment to kind of do this mental math here. Plugging in -2 everywhere. And I choose this example because I know that negatives, sometimes they just like, you know, the brains forget about the negatives. And we really want to make sure we're really practicing that accuracy piece, right? So in fact, this -2, when I cube it, is going to give me a -8. But this middle term here, just like we did above, I'm going to square that -2 first, which is going to give me a +4. And then times 2 is going to give me a +8 minus 1 all over 5. Got to be careful here. -3 times -2 will give me a +6. And I end up with -1 over 11. Now, -1 over 11. Quick question for you all. Is that the same or different as this? Yeah, those are the same. If I have the negative sign on the top or the negative sign on the bottom, those are the same. Is it the same or different as this? Yeah, why is that last one different? it actually becomes positive when we simplify it. Exactly, they are positive, okay? So this last one, we're gonna put a big red X through. The negative on the top and bottom, you can't have both of them. You gotta only have one, okay? Some of us also prefer to write it like maybe we would just do negative in the front and 1/11, and that's okay too, okay? So as long as there's only one sign somewhere there, that's good. But if we have two of them, then we've accidentally made it positive, okay? All right, what does this mean? If you graph this function and you go to -2 as an x value, the y value there is going to be -1/11. Right, that's what that means. Okay, so let's continue on to the second most common strategy that we're going to use, okay? We're going to take a look at factoring. Now, those of you who've had me before, you know I have a deep love for factoring. This is not the same for all students, and I understand that, but I've also yet to be in a math class where I've not used factoring, okay? So whether we like it or not, at some point, it does become a really valuable tool, all right? So we're going to take a look at these examples right here for the factoring, but even though they're in the factoring category, one of the things that makes like quizzes and exams hard is I don't tell you like use this method, use that method. Like I want us to think about the decision. So let's pretend that we didn't know that we were going to be factoring, okay? And so the only thing we've learned so far is that you should just plug in the value and see what happens, right? So let's do that. I'm going to plug in a 1. So I get 1 squared minus 1 over 1 minus 1, which gives me 0 over 0. Okay. Even though we have 2 zeros, one of those zeros is the problem. Which one of those zeros is the problem? All right, we have top, we have bottom, bottom, bottom. Okay. And I ask this because this is like the classic question, right? Like at some point we've all heard the 0 in a fraction is a problem, but then we never really finish that sentence for ourselves. It turns out that it is indeed the 0 on the bottom that is the problem, okay? The 0 on the bottom is the problem. And so when we do this, we evaluate it, we actually end up with an undefined, okay? So if you put it into your calculator 0 over 0, it's going to tell you there's an error. We write that as undefined. This is not the same as saying the limit does not exist. Okay, so sometimes I have students who plug in the value, they're like undefined, the answer is the limit does not exist. But it turns out that if we try some sort of clever strategies, we can actually work through this question, okay? So I'm gonna copy this down here. We've got the limit as x approaches 1 of x squared minus 1 over x minus 1, right? And if we were to factor the numerator, right, the denominator is going to stay as x minus 1, but x squared minus 1 is a very classic version of the x, well, a squared minus b squared. Right? That was something that at some point in your mathematical history, someone was like, this is important. It's important because it shows up a lot, but does anyone remember what does a squared minus b squared factor into?
Is it a plus b, a minus b?
It is exactly that, Nor. Thank you. So we have a plus b and a minus b. All right. And so if we apply that to this x squared minus 1, we would get x plus 1 times x minus 1. Okay. Now, check out what we can do. This x plus 1 is fine, but the x minus 1 on the top, we could reduce that with the x minus 1 on the bottom. And then we could write it like this: the limit as x approaches 1 of x plus 1. Right? So we've simplified the problem a little bit. Now, try plugging in the number again. Okay? So we start with substitution, but we also end with that. If we try plugging in a value of 1 now for x, we end up with 2. Okay. So what does this mean? I'm going to write a sentence here to kind of help us frame that. Okay. 0 over 0 means we have a hole in our graph at x equals 1. Okay. We have a hole in our graph at x equals 1. However, the y value that the spacing. This is the other thing about I do like writing on a whiteboard, but I can't just move things around if I accidentally space it wrong, you know? Okay, so the y value that the function approaches from both sides is 2. Right, so 0 over 0 means we have a hole in our graph at x equals 1. However, the y value that the function approaches from both sides is 2. Okay. I want to do this example. Okay, no. For the sake of time, I'm going to ask us to pick one of these two examples. Would we like to do number 6 together? Or would we like to do number 7 together? Pick your poison. See a couple votes for 7. Okay, great. So let's take a look at 7. All right. We're going to start the same way. We're going to plug in the value and just see what happens. Okay, so I'm going to plug in the value of -1. How do I know that I'm plugging in -1, by the way? Yeah, exactly. I got it from down here, right? The value that x is getting close to, that's where I plug that in. -1 squared minus 2 times -1 minus 3, right? And if we are very careful with our computations, we should end up with 2 minus 3 plus 1 over 1 plus 2 minus 3, which gives you the 0 over 0, and this bottom 0 being problematic, okay? But as soon as we see 0 over 0, we know there is a hole at x equals -1. Okay. Let's factor. So we get the limit of x approaches -1, 2x squared plus 3x plus 1 over x squared minus 2x minus 3. I would say let's factor the denominator first, okay? I think that one is the one that probably we all feel is a little bit easier than the top. And so if we factor the bottom, we should end up with x minus 3 and x plus 1. Okay. If I don't feel good about my factoring, I usually start with the one that seems less complicated, because I bet one of these factors is also going to be on the top. So when these questions are written, people are like, well, we want students to practice how to factor, and we want them to be able to cancel things. So it's likely that one of these factors will also show up on the top, okay? It turns out in this case that when we factor the numerator, we get 2x plus 1 times x plus 1. Okay. This is lovely because we can reduce the x plus 1s. And now we can try plugging in our -1 again, but to a more simple looking fraction. Okay. We plug in our -1, get 2 times -1 plus 1 over -1 minus 3. And I believe we end up with a -1 over -4, which, as someone had mentioned earlier, we have those two negatives, is going to be positive. So we end up with a positive 1/4. So I'll drop another link in the chat. All right. So Desmos, you can do the activities like that we have sort of like today, but oh gosh. Why is this not? Oops. If you go to that, right, and I'm going to share my screen, so you don't have to do that, but this is something, a tool that you might find useful when looking at your, like, helping out with your homework. Okay, so let me, where's my Desmos on here? So if you go to Desmos, it is also a free app. If you're like feeling super nerdy, you can have it as an app on your phone. But what you can do is type in the equations, right? So in this particular case, we had 2x squared plus 3. Let me go back and do this. I'm gonna put parentheses around this. 2x squared plus 3x plus 1. I'm gonna close that parenthesis. And then I'm going to divide it, because that's what the question looks like, x squared minus 2x minus 3. Okay. And so now we have a picture of what this function looks like. Okay. Now, in this particular question, I said, I want you to see what happens when you get close to an x value of -1. And so the beautiful thing about this, you could sort of zoom in a little bit, you can get close to that value, right? So I'm looking at the part of the graph that has our -1. And if you click on that, these little gray dots pop up. And do you see how that says -1 comma undefined? All right, that's technology saying, yeah, you have a hole in your function there. So if you graph it on Desmos, and you can use a graphing calculator too, but I think it's a little clunkier to navigate. If you see -1 comma undefined, right? That's telling you there's a hole right there. And in fact, they do, when you hover right over it, give you an open circle to look at. Now our answer was 0.25, right? So let's imagine I was just tracing my function. I'm tracing from the left. Look at these y values. They're getting smaller and smaller and smaller, but they're getting pretty close to 0.25. And same thing if I come from the other side and I'm like tracing the function this way, it gets closer and closer and closer to 0.25. Okay. And so that's a way that you can check your answers. If you're like, I don't really know what she's doing, how does she know when to factor? If you graph it and you click on the value you're looking at and it says undefined, that means there's a hole there. Okay. So cool things you can do with Desmos. It is free. You can just type in the equations and it'll give you a lot of information. Okay. Yes, Nora, what's up?
So what are we doing with these answers? Like I see like, okay, so for example, we plugged in -1 and then we got 1/4. So that's like a coordinate, but it's like, what is that? What does that matter? Like, what does that represent? Is it important or not?
What do you mean by important?
So like we're doing limits, right? But what is, what I feel like we're doing is we're just taking an x value and just plugging it into the function, right? So it's kind of like, how does the answer relate to limits?
I see. Okay. So let's go back and like write out what this means. So what this means, like what our answer means here is that the y value that the function 2x squared plus 3x plus 1 over x squared minus 2x minus 3 gets really close to when x approaches -1 is 1/4. So it's allowing us to say not just what's happening at specific points, but what happens when you get close to specific points. And this idea of closeness is going to be something that we see a lot over the semester. Like sometimes we can't get an exact answer, but if we can get close enough, that allows us to sort of describe what's happening.
Okay, perfect. That makes a lot of sense. Thank you.
Great. All right. So looks like we've got about 10 minutes left, and I'd love to do at least one of these examples right here. Okay, so let's take a look at another sort of case. All right, so sometimes we'll see things where it's like, oh, we're going to factor here. And sometimes we'll see something where we're like, oh, we're going to need to use like a different method, like factoring might not necessarily work. But we're actually going to start with, why did I start with that question? It's not what I wanted to do. All right, we're going to start with example 9, all right, and take a look at that. But as we look at this, we're saying we want to see what happens as we get really close to x equals 9 for this particular function, okay? And so like a good calculus student, let's plug in the number and see if it actually gives us a coordinate. And it turns out we end up with 0 over 0, with this bottom 0 being the problem. And so therefore, we have a hole at x equals 9. Okay. So since there's a hole, we can't figure out what's happening exactly there, but we want to see what's happening around that area. And so what we're going to do is I'm going to recopy this problem for a moment. The limit as x approaches 9 of square root of x minus 3 over x minus 9. Okay. Now, once upon a time, maybe in like pre-calculus, might have been the last time you saw it, maybe you heard of something called a complex conjugate. It's also okay if you don't know what this word means, okay? They're complex conjugates, and usually we learn those when we're dealing with imaginary numbers, right? So like if I had 2 plus 3i as a complex conjugate of 2 minus 3. Oops, that's supposed to be a 2 minus 3i. Okay. Now, I will tell you also that like 5 minus 8i and 5 plus 8i are complex conjugates. So what is the complex conjugate for 1 minus 4i? Okay, so pattern seeking here, right? Even if we've not seen it before we sort of get scared about the words, all we're doing in the complex conjugate is we're changing the sign in between. Okay, now how does this relate to what we have here? It turns out we're going to multiply by a conjugate. Okay, so we're going to look for the place that has the radical. And if I have square root of x minus 3, what do you think its conjugate is?
Square root of x plus 3.
Yeah, you got it. You keep the outside parts the same, but you change the sign in between it. Perfect. Now, if I write this and that's all I write, I'm changing the entire problem. And that's an issue. What if I do this though? What is this reduced to? Yeah, this reduces to 1. I could multiply something by 1 and I'm not changing it. So it's a very clever trick that we'll see a lot. If we're like, we need to like change the way it looks, but we don't want to change what it actually is, we multiply by 1. Okay. Now, when we multiply fractions, we're going to multiply straight across, right? Good, useful skill to, or technique to remember. And so let's go ahead and multiply this out, okay? We end up with square root of x minus 3 times the square root of x plus 3 on the top. And on the bottom, we end up with x minus 9 times the square root of x plus 3. It turns out we're only going to multiply out this one. Okay. The part of the fraction that had the conjugates, that's what we're going to multiply out. The part that doesn't, we're just going to leave it like that. Okay. So multiply this. I'm going to leave that bottom part alone, so I'm going to go ahead and write that there. What do you mean by factor out the negative sign?
Can you hear me?
Yeah, I can hear you now.
Okay. So the form was like you were saying, the A minus like BI. And if radical is kind of like the I,
Mhm.
shouldn't it be on the right side of the binomial? And
I see
then,
what you're saying. Yeah, so actually the radical is like the A and the number is like the BI.
okay.
Yeah.
Okay, thank you.
Okay, so let's try and multiply this out, okay? If I take square root of X times square root of X, what do I get? Mhm. So just this first part, square root of X times square root of X, I'm gonna get X. Now, this is the part where I think sometimes students are like, but I don't know what the rest of it is. Like when we FOIL something out or we multiply the binomial. If I take the outer terms, I get square root of X times 3. I can just write that as 3 square root X. And I think sometimes for those of us who might feel intimidated, like writing that down, it's okay that you don't know what this is, but if you can say, I'm just multiplying 3 times the square root of X, and you get 3 square root of X, that's okay, right? When we do the same thing with the inner terms, we end up with negative 3 square root of X. And when we multiply the last terms, negative 3 times positive 3, we get negative 9. Okay. Dan was able to jump straight to this answer, which is great. Because when we did it sort of this long way, this plus 3 square root of X and minus square root of, or minus 3 square root of X, that goes to 0. Okay. So what's left in our fraction? In the top, those are the only things left, X and the minus 9. The bottom, which we were very patient and we didn't do anything to it, we just kind of let it sit there. Now I hope it's like, oh, this is why we didn't multiply it out, because those reduce. Okay, if we had multiplied out the bottom, it would have just gotten grosser and grosser, and then it would be hard to see that we could cancel things out. Okay, what's left in the numerator here? Yeah, there's a 1. All right, there's a 1 there. Now let's try plugging in our value again. We get 1 over the square root of 9 plus 3. We do a little bit of computation. We end up with 1/6. Okay. So all of that was to say, if we graph this function and we get really close to x equals 9, the y values should get really close to 1/6. Okay. All right, that is where we are going to stop today. We go ahead and stop this recording.